Okay, is everybody ready? Yeah. This is for you is for Unicode.
Thank you, and thanks for making it out early for the first presentation. All right. Thanks, everybody. As you mentioned, my name is Greg Back. I'm going to be talking about Unicode today. With apologies to Sue Grafton, I'm going to try to make this into a kind of a mystery-themed presentation. So the obvious question to lead off with a presentation like this is, what is Unicode? But we're not actually going to start there. We're going to start with, what is an encoding? Hopefully, if you've been a programmer in the US for any length of time, you've probably dealt with ASCII, a way to represent various letters, numbers, punctuation, suitable for most English text, not all English text. And life is pretty easy when all you have to deal with is Unicode. Or sorry, with ASCII. But if you start having to deal with other languages, it gets a little more complicated. So beyond ASCII, there's an encoding called Latin 1 that adds a lot of accented characters, some more currency symbols, a few other characters that are useful in representing Western European languages. There's another encoding, Latin 2, with some different accented characters. Some are the same. Beyond the Western European languages, you have things like Greek with a different set of characters. Get into non-European languages like Japanese and other Chinese, Korean, have some other characters in that beyond the ASCII character set. Even some 2-byte characters. There's not enough bytes to represent all the characters. So basically, an encoding is a way of mapping characters into numbers or bytes that a computer can understand. So the first clue in our mystery, to solving our mystery, humans deal with characters, but computers deal with bytes. And so an encoding is, how do you map human characters into bytes that a computer can understand? With that understanding, we're ready to say, what is Unicode? Unicode was designed to be a way to represent all of the characters in all of both the active human languages, as well as a lot of historical languages that aren't used anymore, mathematical characters. Recently, all of the emojis are Unicode characters. So Unicode was made to solve this problem of, I have text that is in some encoding, but as we saw on the other slides, the same byte value can mean different things in different encodings. So Unicode is meant to be an unambiguous character encoding mapping from bytes to characters. One, I guess, nuanced thing that's important to realize, if you've ever heard the term Unicode code point, that is sort of like an intermediate representation between characters and bytes. So I want to distinguish between characters, code points, and glyphs. So a character is the idea of the letter A, or whatever character it is. And if you see, you'll see these terms in a lot of the documentation. A code point is how that character is represented as Unicode. And it's typically written with this U+ syntax, followed by a 4 or now 5 character hexadecimal value. This is still kind of conceptual. You don't actually, you don't have code points directly as bytes on a computer. And then a glyph, which I'm not going to talk too much about today, is all of the different ways that you can display that character. So that's more in the realm of fonts and things like that. There is, in an ideal world, there's a one-to-one correspondence between characters and code points. But that's not always true, and we'll get to that in a little bit. But in general, the idea behind Unicode is for each character in any of the languages, there is a unique Unicode code point for that. I mentioned that you can't directly represent code points in bytes. So there are ways to encode a code point into bytes. There's a lot of different ways to do it. These are kind of 4 of the most common. UCS2 is obsolete and you shouldn't use it. Basically, it maps every Unicode, all of the kind of the first set, the first 64,000 Unicode characters to a 2-byte value. UTF-16 uses something called surrogate pairs to represent all of the Unicode characters. And UTF-32 unambiguously represents every code point as 4 bytes. But for a lot of text, using 4 bytes for characters is a big waste. So that's why UTF-8 was developed. It's a variable with encoding. All of the ASCII characters are represented as their 1-byte values, and then all of the other higher code points are represented using 2, 3, or 4 bytes. For all practical purposes, you can basically deal with UTF-8 for almost everything. Windows, you kind of have to deal with some. I'm not sure if it's actually UCS2 or more like UTF-16, but it is very much a 16-bit character on Windows. But for all like web stuff, UTF-8 is pretty much the standard. I'm going to show some code. All of the slides that are blue are Python 2, and all of the slides that are green are Python 3. Tried to make it a little alliterative, so it's easy to remember. So in Python 2, you have your quoted string literal. And does anybody know what the type of this is? String, yep, it's the str type. In Python, you basically have 2 types of sequences of characters or sequences of bytes. Byte strings and Unicode text strings. And you can use a B prefix to explicitly say this is a byte string, and you can use the U prefix to explicitly say this is a Unicode string. And so as we'll see, yes, the first string is an str, and str is the type of byte strings in Python 2. In Python 3, very similar, except, well, it's very similar in that the single or the double quoted string is still the str type. But in this case, the Unicode string is the same thing as a string literal without any prefix. So in summary, Python 2, the Unicode type is called Unicode, and the byte type is called str. And on Python 3, the Unicode type is called str, and the byte string is called bytes. These two make perfect sense. This is very confusing. So this actually isn't a clue in our mystery, but this is one of the important things to remember if you're dealing with both Python 2 and Python 3. Another big difference between Python 2 and Python 3 is how you can combine byte strings and Unicode strings. In Python 2, it just lets you do it. So we have a byte string and then a Unicode string, and we just cram them together, and it's a Unicode string. Python 3 is not so nice. It says, can't do that. So again, summary of the differences. In Python 2, you can add them together. In most cases, some edge cases that I can go into. In Python 3, you can't. So is this a win for Python 2? No, not at all. It lets you get away with things that work, especially when you're dealing with just ASCII, that if you have non-ASCII characters, just start blowing up in your face. So if you've ever been in a situation where your program works and then you suddenly get some unexpected input and then it blows up and you're like, why is this happening? This is kind of a clue towards that. The right way to combine a byte string and a Unicode string is to either decode the byte string into Unicode and then add it to the Unicode string, or to encode the Unicode string as bytes and then add it to a byte string. So in this case, we get the same sequence of characters, but in one case it's a byte string, and in the other case it's a Unicode string. So clue number 2 in our mystery. The process of converting from Unicode to bytes is called encoding, and the process of transforming bytes into Unicode is decoding. I get this confused all the time. I might even say it wrong during this presentation, but remember that. This was another big sticking point for me that once I realized it made understanding this all a lot better. So here we have a Latin 1 string made up of some they're not arbitrary, but some non-ASCII byte values. And we can print out the bytes in a little more clean format to see them. But if you try to encode it as ASCII, you get an error. Not surprising. You've probably seen an error like this before if you've ever dealt with text in Python 2. So here again is the command we ran and the error we got. Python 3 doesn't actually make this any better. It still can't do it, but it does give you a better error message. Oops, sorry. So if you try to call encode on a byte string in Python 3, you get an error saying there's no method called encode on bytes. Python 2 will subtly try to help you out, and in the process create lots of confusion. So again, the right way to do encoding and decoding, if you have a byte string, which is what our Latin 1 string is to decode it from the Latin 1 bytes into a Unicode string. And from there, you can encode the Unicode string as UTF-8 bytes. And so there you can see there's the actual values of the characters. It's almost Unicode, but not quite. So this was probably the most important thing for me to realize. Unicode is not an encoding in Python. If you ever try to encode something into Unicode, you're doing it wrong. Or if you're trying to decode something from Unicode, you're doing it wrong. You decode it to get it to Unicode, and you encode it to take from Unicode to bytes. So our Latin 1 string didn't work in ASCII. So let's try it as UTF-8. We still get an error. But if you notice, this error is a little bit, it's the same error we got before. It's saying the ASCII codec can't decode that byte. Why did it do that? We wanted UTF-8, but it's saying we can't do ASCII. If you look closely, you see that we tried to do an encode, not to mention the fact that it's already a byte string. So that's one problem. But we get a Unicode decode error. What's up with that? The reason is that Python 2, behind the scenes, says, OK, you're trying to encode something that's already encoded. So I'm going to decode it for you first, and then encode it. And the system default encoding on Python 2, in many cases, is ASCII. So it's trying to decode the string as ASCII before encoding it as UTF-8. And it fails because we have these non-ASCII characters in our byte string. There's a bunch of things you can call to deal, or a bunch of attributes and functions you can call in the standard library to get information about the types of encodings that are used on the system. This is a handful of them. As you see, some of them are UTF-8, some of them are ASCII. There are ways to set the default encoding to something other than ASCII, but I've never gotten them to work reliably. They've always caused more problems than it's worth. So it's better to be explicit with your encoding and decoding so that you know when you're encoding to and from Unicode. Python 3, it's a lot cleaner. It's always UTF-8. So that's definitely a win for Python 3. So again, summary. Python 2, ASCII most of the time, that you can change it. Python is UTF-8. And then that sys get default encoding, you probably never actually need to call it because it will be these things unless you're on a system that isn't using ASCII. So just to prove to you that you can do encoding and decoding correctly in Python 2, we have a byte string here, and we're going to decode it as Latin 1 because we know that's the encoding of it. And then we're going to encode it from the Unicode back into UTF-8. And see, no errors. It worked. The next clue to deal with encoding and decoding is, I didn't come up with this term, but I call it, it's called the Unicode sandwich. And basically, if you have your code, you want to decode from bytes to Unicode as soon as you can, and deal with Unicode throughout your program, and then only encode it to bytes at the very end when you're outputting it to somewhere else. Fun fact, when I was writing this slide, I had encode as the first one from bytes to Unicode. I told you I get it screwed up, and I just caught it like an hour ago. So we know that encodings are important, because if we have a stream of bytes, we want to get it into Unicode. So natural question, how do you know what the encoding is? There's a few answers to this question, so we're going to go through them in order. You don't. If you have a stream of bytes, it can be any encoding or it could be no encoding, and maybe it's not even text. Unless you're told. HTML, HTTP, XML all have ways of specifying an encoding. Even Python source code has a way of specifying the encoding for a stream of bytes. You can't always trust it, though. If you're on a web server, sometimes if you're on like a shared hosting environment, if you're don't have control of the web server, it'll return an HTTP header with one encoding, even though your HTML is in a different encoding. Lots of work in web browsers goes into detecting the encoding and displaying it correctly. But even then, you have probably gone to a web page where it just looks like gibberish. Hopefully not recently, but it used to be a much bigger problem. Fortunately, like I was mentioning with the web browsers, you can usually guess at the encoding. There's a great third-party Python library called Chardet, or I don't know how you pronounce it, but I pronounce it Chardet, that given a string of bytes, you can tell Chardet to detect the encoding of the string. So we have 2 byte strings here. They're completely different. One of them is in an encoding called GB2312, which is used for a lot of Chinese characters, and the other one is UTF-8, according to Chardet, with 99% certainty. So let's try it. If we think there's the encoding, let's try decoding them. Success. It was actually the same string all along, surprise. A twist in our mystery. If you try to decode with the wrong encoding, you're going to get errors. In this case, I just switched to the 2 encodings. I tried to decode the first string with UTF-8, and I tried to decode the second string with the GB2312, and I got these exceptions. Anytime you get exceptions like this, it's probably a sign you have the wrong encoding. There is a workaround, which is there's a second option you can pass to the decode function, which is what to do if you get a byte that doesn't match the encoding. You can either just ignore the error, you can put in a substitute replacement character, you can escape it with certain escape codes. I don't have a slide that actually lists them, but if you look up the documentation for the decode function, there's a handful of ways you can deal with errors. The problem is that if you have the wrong decoding, you can replace and still get absolute garbage. So don't do that. That said, sometimes you do have to do something like this. If you have just poorly formatted text or text that naively combine things in different encodings, it may not be possible to decode perfectly a given byte stream under any encoding. Encodings are hard. One other caveat with this. It's not perfect. I have another byte string here. It says it's Max Cyrillic, and it's in Russian. It's not actually. It's actually using this CP 1251 encoding. The only difference is that first character. I don't speak Russian. I don't really know Cyrillic, so I have no idea what that actually says. But Chardet is not perfect. Is the point of this. Yeah, I did look it up on Google Translate, but I don't remember what it was. It was economics and something. I don't know. So the 5th clue is be prepared for anything. You really never know what you're going to get with text that you get from somewhere. One other quick gotcha with Unicode is normalization. So we have 2 strings here, and we're going to see whether those 2 strings are equal. Let's take a poll real quick. How many people think that first thing is going to be true? How many people think it's going to be false? I wouldn't have put this in here if it was true, would I? It is false, yes. And as you see in the second box there, they have different lengths, and they have different byte values. And the reason for that is, remember how I said that Unicode tries to map one-to-one characters to code points? That is not perfect. And so the first string, there is a Unicode code point for the E with the accent. And there's also 2 other Unicode code points for the E, and then the accent combined with the previous character. So that way you can put a accent on any character that you want. The problem is if you're using something like this for usernames, you could have 2 people that have what looks like the same username, but it's completely different Unicode. There is a feature in the standard library in the Unicode data module that lets you normalize all of your text to the, so NFC, I forget what it actually stands for, but basically it means combine if you have any instances of the combining accent characters, combine it into the single value. And so when you're doing comparison on things like usernames is the best example, make sure you're normalizing the input first. One other quick, I guess, hint in the standard library is that there are some functions that behave differently if you pass them byte strings versus Unicode strings. So the lister command or method in the OS module, if you pass it a Unicode string, it will return you all of your paths as Unicode strings. And if you pass it a byte string, it will return you values in byte strings. This is actually useful for most applications because you have something and you want to deal with the same thing. But if you don't know this is happening or don't expect it, it can cause a little bit of confusion. Everything so far I've been talking about is if you're in Python 2 or if you're in Python 3. This is how you handle it. Sometimes you're writing code, if you're writing a library or a package, that you want to work on both Python 2 and Python 3. There's a compatibility library called 6. If you're not using it and you're trying to write Python 2.3 compatible code, you should anyway. For no other reason than it makes handling text much better. So there's a variable called 6 text type, which is on Python 2, it becomes the str type. And on Python 3, on Python 2, it becomes the Unicode type. And on Python 3, it becomes the str type. Binary type is str on Python 2 and str on Python 3. And then string types is good to use in instance checks, or just on Python 2, it's either of them, and on Python 3, it's just the Unicode type. These are useful, like if you normally have a call to str, you want to convert something to a string. You can use this instead. You say, I want it as text. And that's a lot more, it works better between Python 2 and Python 3 than just naively calling str, because on Python 2, you'll get a byte string, and on Python 3, you'll get a Unicode string. The other kind of key to working with Python 2, Python 3 compatible code is the future import Unicode literals. One thing that confused me for a while with this is this only applies to literal strings in your Python code. It doesn't magically solve all of your Unicode problems. But normally, if you were to run that second command there without running this import, it would be the str type. But now it's a Unicode string. So use 6 and use this import. That is the, oh, there it is. I had a slide for this. Use the 6 module and use Unicode literals for cross-compatible Python source code. So hopefully those 6 tips, along with some of the other notes I had along the way, were helpful. This is my last slide. I'll let everybody take a picture of it. It seems like everybody wants a picture of this one. Here are some of the resources. I will post these slides afterwards and probably send a tweet to PyOhio, so it'll get copied there. I'll go back to this so you guys can look at it. Does anybody have any questions? On Python 3, yes, because they'll. So like for that cafe example, you like did a string compare with that return true? No. So that works the same way in Python 2 and Python 3. Where you can get in trouble is if you try to compare a byte string and a Unicode string.
But no, like when you had the cafe example.
Yep.
Underneath they were different. But if you did like a string compare on those two strings, it would return true. I'm assuming you created them differently.
Yeah, I created them differently. I actually had to type. I made the byte string and then printed it out to get the variable to paste in. Or if you can enter those characters on your keyboard, you can do it that way too.
If I was to copy that word cafe somewhere on my computer,
yep.
web browser, Microsoft Word, I don't know, can I be sure of which of the two I could get?
No.
Or is that going to be a mystery too?
It will probably be a mystery. It's possible that some software will normalize it when you paste it, but I'm not actually aware of any that does. Yeah, so I don't have any good advice. In my experience, most of the Python libraries for like the database driver libraries, so MySQL libraries, MongoDB libraries, all do the right thing if you pass them Unicode strings in Python 2 or Python 3. There are ways to configure the database so that all of the text fields are in Unicode or UTF-8. It varies what it's called, but basically it's stored as UTF-8 bytes. And then the drivers, when you pull them out of the database, will return you Unicode strings. And so that kind of handles that part of the sandwich for you. In terms of accepting input from users on a web form or whatever, you really have to be explicit and do the conversion to, you want to make sure that you are consistent in what you pass to your database or whatever. Does that help? Or
I've had lots of experiences with string Microsoft characters.
Yeah, so that generally happens with, I think if you have, I'm trying to remember now, if you have UTF-8 text and it gets interpreted as Latin 1 or vice versa, a lot of those characters are typically, I have decimal up here, not hex. But a lot of times you'll get that 233, that E with the accent, because that is usually the first character of a lot of 2-byte UTF-8 values. I have lots of examples, not in the slides, unfortunately, of that kind of mixed encoding that results in gibberish text. If you can be confident of the encoding that's coming in, you can generally do the right thing with it.
Yeah, I was just going to add, because if you get UTF-8 given to you, but you store it with Latin 1, that's valid, Latin 1, even though you're getting all these funny characters in there. So you'll have extra characters in there until you reconvert it back. So Latin 1 is usually a kind of a hack way to get data moved that is UTF-8 encoded back from, say, the database or something like that. We've had to do that often where it got put in wrong and you're going to have to tell the database, well, how do I get it out? Well, switch to Latin 1 to get the bytes back. And then you're going to have to know what the real encoding is. Because we've done it with Russian, with Chinese, and so forth, where it got stored in as raw bytes, and then you need to pull it out somehow in Python, and then you got to know what it is ahead of time.
Yeah, that's actually a really good point. That's something I didn't mention in my slides. A lot of the Latin 1, Latin 2, Latin 3 encodings, any byte is valid. Almost, yes. You get like null bytes, and there's some holes in some encodings. I think Latin 1 might actually be.
There's like 5 characters
are there?
that are technically not legal. Yeah.
Okay. But yeah, so if you try to decode, you can decode most things as Latin 1, even if they aren't Latin 1. That's a problem to keep in mind. Any other questions? Yeah.
I want to add one more thing we bump into is you can double encode UTF-8, and that'll cause you a lot of pain in English.
Yeah.
So don't just always encode UTF-8 arbitrarily, because if you already have UTF-8 and you encode it again, you'll cause oddball things to happen.
Yeah. A few more things. In case you want to know all of the Unicode characters I used, here was a few of them. Fun fact, though, the thumbs up and thumbs down in my slides are actually images, because for whatever reason, when I'm in presentation mode, it shows them as boxes. Who knows? That's where those are actually examples of the 5 hex characters. You have the leading one for there's different. They're called planes of the Unicode character set, or of the Unicode character space, I guess. And so all of the emojis are like the 1F ones. There's all of the characters in that one Latin 1 string. As you see, they are all basically 00 something characters in the Unicode code point space.
Suppose you wanted to create in your program a Unicode string with those characters down there. How would you physically do that?
That is a great question, and I should have put this in my slides because it's probably very common. You can do \u and then those 4 values. as a string in a string literal. That's another way. There was the question about how I got those 2 cafe strings. You can also, in place of any, I mean, even ASCII characters, you can do \u, and then 4 hex characters. You can also, I think, do a capital U with 8 characters that lets you do the higher ones. Oh, yeah.
I was going to ask, back on the Latin 1 page, I noticed it had the copyright symbol. Is that actually considered like a Latin symbol, the 169?
169. So, I mean, it is a symbol. It is a character in the Latin 1 encoding. This is, I mean, it's an ISO standard that has a bunch of byte values. It's mostly for the Latin 1 characters. There's a lot of weird punctuation. Like there's that 172 paragraph symbol, the fractions, things like that. It's not all. They had to fill it in, or I guess they didn't have to fill it into something, but they had all these bytes left over, so they put some common.
What does it mean when the 173 and 160 there's these spaces that look like?
Those are not printable characters.
Okay.
And I forget what they actually are. So 127 is delete, and that's true in all of the encodings. But it's not a printable character. I had a script that did this, and I didn't bother handling all the exceptions, or all of non-printable characters. Did you have a question? Or?
What can it's a random question, sort of off here. Can I have variables for non-ASCII characters?
Yes. Python 3 so the default encoding for Python 3 source code is UTF-8. So you can have variables with any valid code point. I've never actually seen it done. I guess if you're working on a project with people who aren't Americans and have to deal with English, you can probably get away with it. But, so one last thing I wanted to mention. This was originally the title of my presentation. Unicode lets you do some really crazy things. So we have some text here. You can have characters with double strokes. You can have characters with all surrounded in bubbles. You can even do some absolutely crazy things that are almost readable, but don't do this. Please don't do this. It's good for a laugh, but please don't do this.
So those are actually different encodings. It's not simply the same different fonts displaying the same.
Correct. So these are different Unicode code points. So the O, the lowercase o in the first one is different than the lowercase o, a different Unicode code point, and a different Unicode code point than in all the other examples. There's a lot, I mentioned the Unicode data library because that's the one that can do the normalization. There's a lot of properties of each Unicode character. So there's like what type of character is it a letter, is it a number? Because even in all of the other like African languages, Asian languages, they have characters for numbers that are different than our Arabic numerals. But they have a number value, and the Unicode data library stores information about the numerical value of all the characters as well. And I think, but I'd have to double check, that there's something that says the O with the circle is conceptually similar to the letter O, but I'm not 100% sure of that. That's good. I know very little about fonts, but I do know that some computers will have a way of, if you're using a font that doesn't have a glyph for a particular Unicode character, it will go and find a different font on your computer that has that in order to display it. But it's good to know that there's a font that has all of them. Oh, I'm sure, yeah. Yeah, that's really impressive. The other thing that reminded me of, and now I just forgot it. I don't know. I don't know.
Two things. area will cover many of them because it's got a Unicode variant. So as a default, if you're on Windows, that's one to use. But yes, there's probably one that covers all of them, which might be why it's such a preference as well. That some of the dead languages may not be covered. The other thing I want to point out though was Latin 1's important, but you'll run into Windows 1252 encoding because Windows in their infinite wisdom changed about 8 characters in the whole thing, and the Python library will get you if you have those characters. Smart code being one of them, that kind of stuff. M dash, N dash.
Oh, yep.
Those
So
are, yeah.
I have a snippet of code that I just basically write all of those to their Unicode values because.
Right, that's one way to do it a lot of times too. But you'll pop into that a lot. So Latin 1's nice to have as a kind of a go-to, but Windows 1252 is going to pop up a lot more often with Windows users and Mac, and we're copying pasting stuff from Word.
I do remember what I was going to say. So the Unicode standard, the specification, does have basically images for all of the characters. So like what this, a representative glyph for this Unicode code point. But font support is mixed, obviously. And a lot of, if you're designing a custom font for your cool little graphic thing, you probably don't need to put all of the Unicode code points in there. Any other questions? A font is basically a collection of glyphs. It's a mapping between the code point and a glyph for that code point. I don't know a lot about fonts.
This is kind of a comment. I remember back in grade school, there was a time when my classmates and I figured out to retrieve the Unicode letters using Microsoft Word, and we would play around with it as long as we could, trying to find everything.
Yeah, so there's a way. There's a way to enter Unicode characters directly. I know on Mac you can set up a special keyboard that does use Alt and then type the 4 hex characters. There's something that's similar on Windows. I don't remember what it is. The number. It's the number pad on Windows. Yeah, I remember that now. So yeah, there's different ways to enter Unicode characters directly on the keyboard. A lot of times, I'll be honest, I type the name of the character and then find it online and copy and paste it. It worked pretty well, as much of a workaround as it is. I actually did write a script that will, so in order to get these, I wrote a code that would basically print out the names. Like you pass it a Unicode string and it looks up the names of all the code points to print that out. So there are ways to do that too. Any other questions?
I've never heard the name Solidus before.
Yes, that is the official name for the slash, and the reverse solidus for the backslash.
I thought the load line was called an underscore. Is it used differently in this situation?
I don't believe so. I mean, that is the kind of the ASCII underscore. The other thing, I guess, one thing that I will mention is there are a lot of times that the same or very similar glyph is used for multiple characters. So for example, the Greek letter omega, capital omega, is also used as the symbol for ohms, the resistance. But there's a special Unicode code point for, I think it's called ohm. And it looks exactly identical to the Greek capital omega. But they're different code points, but they're very often use the same glyph. Another thing to be careful of. And normalization won't help you with those, I don't think. So you're kind of on your own.
Speaking of things that look the same, there have been instances of people making web address URLs with Unicode characters that look like Microsoft.com or whatever, but are different Unicode characters that just happen to display the same.
Yep, that's a big issue with I think the Cyrillic characters. So Cyrillic alphabet has many characters that are, they look identical to the Latin characters. But because they want to have like the entire Latin block and the entire Cyrillic block, it's not like they reuse the Latin. I think like there's like the Turkish I or something like that too. It's the same thing. So it's not like they reuse the Latin one for that character set. They kind of have the whole block for the entire character set for that language. And so that is a big issue. I know that there are I know the web browsers have been trying to figure out how to combat that. Other questions? All right, thanks everybody. That adds a lot of accented characters, some more currency symbols, a few other characters that are useful in representing Western European languages. There's another encoding Latin 2, with some different accented characters. Some are the same. Beyond the Western European languages, you have things like Greek with a different set of characters. Get into non-European languages like Japanese and other Chinese, Korean, have some other characters in that beyond the ASCII character set. Even some 2-byte characters. There's not enough bytes to represent all the characters. So basically, an encoding is a way of mapping characters into numbers or bytes that a computer can understand. So the first clue in our mystery, to solving our mystery, humans deal with characters, but computers deal with bytes. And so an encoding is how do you map human characters into bytes that a computer can understand. With that understanding, we're ready to say, what is Unicode? Unicode was designed to be a way to represent all of the characters in all of syntax, followed by a 4 or now 5 character hexadecimal value. This is still kind of conceptual. You don't actually, you don't have code points directly as bytes on a computer. And then a glyph, which I'm not going to talk too much about today, is all of the different ways that you can display that character. So that's more in the realm of fonts and things like that. There is, in an ideal world, there's a one-to-one correspondence between characters and code points. But that's not always true, and we'll get to that in a little bit. But in general, the idea behind Unicode is for each character in any of the languages, there is a unique Unicode code point for that. I mentioned that you can't directly represent code points in bytes. So there are ways to encode a code point into bytes. There's a lot of different ways to do it. These are kind of 4 of the most common. UCS2 is obsolete, and you shouldn't use it. Basically, it maps every Unicode, all of the kind of the first set, the first 64,000 Unicode characters to a 2-byte value. Both the active human languages, as well as a lot of historical languages that aren't used anymore, mathematical characters. Recently, all of the emojis are Unicode characters. So Unicode was made to solve this problem of I have text that is in some encoding, but as we saw on the other slides, the same byte value can mean different things in different encodings. So Unicode is meant to be an unambiguous character encoding mapping from bytes to characters. One, I guess, nuanced thing that's important to realize, if you've ever heard the term Unicode code point, that is sort of like an intermediate representation between characters and bytes. So I want to distinguish between characters, code points, and glyphs. So a character is the idea of the letter A, or whatever character it is. And if you see, you'll see these terms in a lot of the documentation. A code point is how that character is represented as Unicode. And it's typically written with this U plus.
Okay, is everybody ready?
Yeah. This is Greg.
For U is for Unicode.
Thank you, and thanks for making it out early for the first presentation.
Put that one out there.
All right. Thanks, everybody. As he mentioned, my name is Greg Back. I'm going to be talking about Unicode today. With apologies to Sue Grafton, I'm going to try to make this into a kind of a mystery-themed presentation. So the obvious question to lead off with a presentation like this is, what is Unicode? But we're not actually going to start there. We're going to start with, what is an encoding? Hopefully, if you've been a programmer in the US for any length of time, you've probably dealt with ASCII, a way to represent various letters, numbers, punctuation, suitable for most English text, not all English text. And life is pretty easy when all you have to deal with is Unicode. Or sorry, with ASCII. But if you start having to deal with other languages, it gets a little more complicated. So beyond ASCII, there's an encoding called Latin 1. UTF-16 uses something called surrogate pairs to represent all of the Unicode characters. And UTF-32 unambiguously represents every code point as 4 bytes. But for a lot of text, using 4 bytes for characters is a big waste. So that's why UTF-8 was developed. It's a variable with encoding. All of the ASCII characters are represented as their 1 byte values, and then all of the other higher code points are represented using 2, 3, or 4 bytes. For all practical purposes, you can basically deal with UTF-8 for almost everything. Windows, you kind of have to deal with some. I'm not sure if it's actually UCS2 or more like UTF-16, but it is very much a 16-bit character on Windows. But for all like web stuff, UTF-8 is pretty much the standard. I'm going to show some code. All of the slides that are blue are Python 2, and all of the slides that are green are Python 3. Tried to make it a little alliterative, so it's easy to remember. So in Python 2,